So, hello, we are the Polish team and we are going to present our solution to the 2019 IMMC challenge. So, we were posed with the task of finding Earth's capacity for human life. So, it's an important problem as for the past few years, climate change has been becoming more and more of an issue. So, as you can see, over the past half of a century, the population of the Earth has grown to nearly 8 billion people. 8 billion people, okay. And so this caused a few problems in a few categories. So many people don't have access to food or water. We overexploit the natural resources of our planet, and also people live in below standard conditions.
So we've divided our problem to 3 smaller tasks to effectively solve it. So firstly, we had to identify factors which significantly affect human population. Then, using these factors, we had to calculate current Earth carrying capacity, and using knowledge from the 2 previous questions, predict how it will change in the future and find the best way to increase it. To illustrate common misconception about Earth carrying capacity, let us consider a thought experiment. There are 3 eggs in a 6-position egg box. If we eat one of them and then put one back in every day, the size of the egg population will remain the same at 3. So, what is the carrying capacity of the egg box? Is it 3 or 6? We think it's 6, of course, because 6 eggs can fit into the box, and 3 is population equilibrium. We made 2 main assumptions at our model. There are both that trade of resources and time spread of our data is negligible.
Our model deeply relies on the so-called safe and just space. It is a framework proposed by Kate Raworth in 2012. It focuses on sustainable environmental development while maintaining decent life for all people. It forms a donut-shaped space bounded by planetary and social boundaries. This bounded area, also called safe operating space, for people is a space for people to live happily while not damaging the environment. For us, the Earth's carrying capacity is the maximum population that can live within the safe and just space. Based on the safe and just space, we selected 10 key factors. We divided them into 2 groups: biophysical factors, which are CO2 emission, nitrogen emission, phosphorus emission, material footprint, and water footprint. The other group is social factors. These are nutrition, percent of population living in poverty, education, access to electricity, and access to clean water.
So, there were many attempts to solve this problem in the past, and they came up with completely different and varying results, as you can see in the graph here. And this shows that the assumptions that we make are very important to the results. But nonetheless, the most common answer was 8 billion people. So first, we considered a few models. Our basic model was taking the amount of a renewable resource that was available and then dividing it by the amount of the resource needed per person. And that gave us the carrying capacity. So we did it for a few factors, including water, nutrition, and area. And we came up with 3 numbers for the following factors. Water was 31 billion people, food was 13 billion people, and land was 12 billion people.
Our main model is based on one observation, that the key factors are interdependent. That means that, for example, change in population induces change in CO2 emission, which further induces change in material footprint, and so on and so forth. In dynamic model, we combine the notion of safe and just space with system dynamics. System dynamics is an approach that enables us to calculate the behavior of a given system of interdependent elements. First, according to safe and just space, we set certain thresholds that our key factors must not exceed. Next, using a Python system dynamics library, we were able to create a code that calculates what maximum population fits in the safe and just space. The graph here is a simplification of the system used in our model. We calculated the carrying capacity for each country separately and combined our results. The final answer we got out of the dynamic model was 7.6 billions. We are of course aware of the strengths and weaknesses of this model, with the strengths being that it takes interdependence into account. It includes social factors as well. The Earth's carrying capacity is calculated for every country separately, and it allows for analysis of what role each factor plays in changing the carrying capacity. The weaknesses of this model are that economic processes are not considered, and we lack exact insight into calculations made backstage by the Python library.
Our final goal was to figure out a way to increase carrying capacity as efficient as we can. So we found 10 innovative technologies we can change the world in the nearest future, such as cold fusion, liquid cold, or plastic decomposed bacteria.
So now let us introduce the precedent model. Precedent model is based on a combination of probability decision trees and Q-learning algorithm. In this model we simulated a world leader, the president, who can make decisions that impact the real world. This way we can see the combination of decisions he can make to raise their carrying capacity. In precedent model, creating an artificial environment is crucial. Therefore, we try to many different possible scenarios. Q-learning approach fits to this problem perfectly because of its simplicity in application, fast learning time, and ability to adapt to the new environment given set of rules. In our model, we used Q-learning reinforcement algorithm. The goal of the Q-learning was to learn a policy which would tell the president what action to take under what circumstances. For any set of the strategies, Q-learning finds a policy that maximizes the expected value of the total reward, in our case, Earth's carrying capacity. For our model, we created an environment which is representation of these strategies, where each has an impact on Earth's carrying capacity. Precedent model left us with an average 70% increase in the future Earth's carrying capacity, which gives us 30 billion people that our Earth can hold. So that's all of us. We are open to any questions.